Okay, in this video we'll be continuing with circular motion. More specifically, we'll be talking about vertical circles. Now, when we talk about vertical circles, usually we are referring to our roller coaster scenario. Now, if we imagine our roller coaster where we have those big loops, like so, and on that roller coaster we usually have our little cart thing, right, that goes on the roller coaster and that the people are in. Now, in NCEA Level 3, you need to analyze the forces that are acting on this cart. So we can see these forces that are acting on the cart in three still positions. The first one being when the cart is at the top of the loop, like this. We can call this position 1. The second one being when the cart is on the side, like so. And the third is when the cart is at the bottom, like that. So now just focusing in on the first scenario. We know that for any object to move in circular motion, there must be a centripetal force provided. Now again, remember, the centripetal force is always provided by a net force. It is not a force in and of itself. Now in the case in circular motion, the Fc is always provided by the net force that is acting towards the center of the circle. And so in this scenario, whatever net forces are pointing directly inwards in our vertical circle, that is the force that is going to provide the centripetal force. So in this first scenario, the cart is going to have a weight force directly acting downwards, and also the cart is in contact with the track, and so the track is going to provide a normal force. So the track is also going to provide a normal force as so. And so in position 1, the centripetal force is equal to the normal force plus the weight force. Right, and that makes sense because these two forces are acting towards the center of the loop. Now looking at our second scenario right here, our weight force is still going to be acting downwards, obviously. So we have our Fw right here. Now because the cart is now on the side of the loop, the normal force is now going to be as so towards the center, right? And so now the only force that is acting towards the center is the normal force. And so for our second scenario, the centripetal force is provided entirely by the normal force. And so our Fc is equal to our normal force. Now for our third scenario, again the weight force is going to be acting directly downwards, as so. And now because we're at the bottom of the loop, the normal force is going to act directly upwards, as so. And so what this means is that for our third scenario, the centripetal force is equal to the normal force minus the weight force. Now the reason why we minus the weight force is because the weight force is directly opposite to the normal force. So the normal force is acting upwards and is providing our Fc, but the weight force is acting directly opposite to that. And so if we remember, our centripetal force is the net force acting towards the center of the loop. And so in order for the normal force to provide a net force, it must overcome the weight force. So the normal force must be greater than the net force in order for it to provide a centripetal force. And that's why we minus our weight force off the normal. Okay, so discussing point number 1 further. If we draw this down here, our first point was saying that the centripetal force is equal to the weight force plus the normal force. Now in level 3, you'll hear this term called minimum speed. And so what that essentially means is the minimum speed required for the cart to go around the loop. You can imagine that if we start up here and we come down and we don't have enough velocity, we're just going to fall off the track like so. And that would be very painful. Probably might die because you might flip upside down. Similar scenario, if we start up here again and we come up here and we get to the top but still don't have enough speed, we are again going to fall down like that. And again, probably die because we're going to land on our heads. And so what the minimum speed is the lowest speed required for us to just barely make it past this top and to come all the way down. And at this point, our normal force is equal to 0. And so what that tells us is the track is not providing a normal force, and so our wheels are just barely touching the track to get us back around. So we're like barely just not falling off. It's the minimum speed, we're just getting by. And so that means if the normal force is equal to 0, that means our centripetal force is equal to our weight force. And we know that our centripetal force is equal to mv squared over r, and we know our weight force is equal to mg. Now, because we have the same mass on both sides, we can cancel those out, and we get v squared over r is equal to our g. And therefore, v squared is equal to gr, and our v is equal to square root gr, as we square root both sides. Now, a key thing to note about this equation is that the mass of the cart has no bearing on the minimum speed. The minimum speed is only determined by the radius of the vertical loop, because g is constant everywhere, right? So the only thing that is determining the minimum speed is the radius of the vertical loop. Now, this actually makes intuitive sense if we think about two vertical loops, one massive one like this, and then one very small one like this. We can imagine that the minimum speed required to go all the way around this big one is going to be a lot larger than the minimum speed required to just go around that tiny one right there. Right? Now, another discussion point is our third scenario. In our third scenario, that is when our cart is at the bottom, just a reminder. And so if we take our third scenario, that is when our Fc is equal to the normal force minus the weight force. If we just rearrange this equation, we get our Fc plus our weight force is equal to our normal force. And so what that tells us is that when we have our loop and we have our cart at the bottom, the normal force is largest at this point. The reason why this is significant is because the normal force is what gives us our sensation of weight. It's not the weight force that gives us our sensation of weight. The normal force is the force that the ground provides that is accelerating us upwards. The reason why we know that this is the force that's giving us our weight is because if you imagine, if you're orbiting around Earth in space, you still have a weight force, but you feel weightless. The reason for this is because you have no support force around you provided by the ground, and so you feel weightless. And so if the normal force provides us our sensation of weight, and the normal force is largest at the bottom, if we go on a roller coaster and we go on those vertical loops, we feel the heaviest at the bottom. The reason why this is significant is because, as the normal force is largest at the bottom, this is where the track is most likely to break. Now, don't worry, I'm pretty sure these are engineered pretty well and they probably won't break. Probably. But this is where the track is under the most stress. And so at the bottom of the roller coaster is where the roller coaster is most likely to break. Some other scenarios where we can see the same vertical circle situation is where we have a little guy, let's call him Timmy. And Timmy has one of those toys where we have a ball at the end of a string, and he is swinging it around in a circle, like this. Now at the top, again, this is our scenario 1, and in this scenario, the centripetal force is equal to the weight force plus the tension force. So the weight force on the ball, right? And also the tension on the string, like so. Now again, we can still use the same concept. So if we want to get our minimum speed is when we can swing this ball all the way around and the string still remains taut. If the string becomes loose and it collapses in on itself, that's the equivalent of us falling off the roller coaster. So we want the string to still remain taut. And that's the same scenario where our weight force of the ball is equal to our centripetal force. Now if we move on to the point where we are at the bottom, again, this is where our centripetal force is equal to the tension minus the weight force. And so therefore the tension is equal to the centripetal force plus the weight force. And so, just like on the roller coaster with the normal force, the tension force in this rope is going to be largest at the bottom. And therefore, it's more likely to break at the bottom because the tension in the rope is largest. Now, if you've ever played with these toys in real life, you would know that when you swing these around and you do break them, they never break on the way up. They only ever break on the way down because there's the most tension on the bottom. And so yeah, that's all you need to know for vertical circles. Sweet.